Hi dear students, a very warm welcome to Ritu Garg Maths classes. As we had discussed in the previous video that we had discussed all the properties of determinants. So now we are going to verify those properties with the help of some questions. So I've taken an example 12. The determinant is given to be like this. I'll be solving using properties of determinants. As you can see that I can go for R1 goes to R1 plus R2. That is, all the elements of first row will be added to the second row elements. So I get x plus y plus z, corresponding elements will be added. Here it is y plus z plus x, that can be written as x plus y plus z. Here also I am getting the same element x plus y plus z. Since R1 was taking the transformation, so R1 has transformed and there will be no change in R2 or R3. This I have used the last property of determinants, property number 6, how to use the elementary transformations. Now, we had discussed in properties that any common factor can be taken out from any of the rows or any of the columns. So, I can see a common factor out, x plus y plus z, from the first row. 1, 1, 1. This is the first row now. Then these. Since x plus y plus z is a common factor out, it remains as such. But here I am getting R1 and R3 as the same having the entry. You know, the identical entries. So the whole determinant vanishes because R1 and R3 are identical. And one of the properties of determinant says if any two rows or any two columns are identical or proportional, the whole determinant will become 0. So anything multiplied with 0 is 0. That is the answer. Next, I have taken the question of example 13. Determinant is given to be this. We have to solve for its value, but I will not be going for simple expansion. I will be using properties of determinants. Here, no common factor I can see, but I can see 1, 1, 1 in the whole first column. So in such a case, we try making as many zeros as many possible. So I'm going to operate R2 goes to R2 minus R1. At the same time, I can go for the operation R3 such that R3 minus R1. Only R1 will be subtracted in both the operations. Since R1 is being subtracted over here, so R1 cannot take the transformation in the same step. Please be careful, okay? So it means I am not having any transformation in R1. So let me write R1 as the same. There is no change in R1. Now I am going for R2 such that R2 minus R1. All the corresponding entries will be subtracted. 1 minus 1 gives you 0. B minus A. Next entry is CA minus BC. And now let's go for R3 such that R3 minus R1. All the corresponding entries of third row and first row will be subtracted. 1 minus 1, 0. C minus A. AB minus BC. Here we can take some common factors. For example, in the last column, if we factorize it, I can see C common into A minus B, and here we have B common into A minus C. Looking further into this question, if you carefully look at the second row, the first entry is 0, second entry is B minus A, and the third is A minus B. So I can actually take A minus B common. And in the third row, C minus A minus C. So you can take C minus A common or you can take A minus C common. It's up to you. So first row as such. It is the properties of determinant tell us that we can take any factor common from any of the rows or any of the columns. So simplifying this, second row becomes 0. B minus A was the factor present over here. I have taken A minus B. It means this is replaced by minus 1. The last term C into A minus B, it has come out. Last row 0. C minus A is the factor present over here which have been taken out. And the last entry is B into A minus C. The negative is changed. So it is minus B. Either you can go for expansion now or you can go for some more operations. I will be writing down R3 such that R3 plus R2, so that it gives me some easier value. The very first two rows will remain as such, there is no change, and the third row is going to be added into second row. 0 plus 0 is 0, 1 minus 1 again 0, and this is minus b plus c, that is c minus b. In such a question where the lower triangle is 0, when I say lower triangle is 0, it means all the entries below the diagonal are 0. Then you can expand and check the determinant's value will simply be the product of the diagonal entries. It can happen with the lower triangle or with the upper triangle also. So it will be 1 into minus 1 into c minus b. That becomes minus minus plus. So if I rewrite it, it becomes a minus b, b minus c into c minus a. This is a simple question, but at the same time very important question using properties of determinants. Let's come to another question. Question number 10, first part from exercise 4.2. It says we have to prove this whole determinant is coming out to be 5x plus 4 into 4 minus x whole square. It's a very important question for 4 marks. Let's start with the proof. I will start the proof with LHS. You have to note down the entries very carefully. All the elements should be written down very well. Now I will have a look on RHS. Where do I have to reach? The very first factor says 5x plus 4. If I add all these rows corresponding elements, I will get x plus 2x plus 2x, that is 5x plus 4. Same here and the same here. So I have got my operation very first, that R1 goes to R1 plus R2 plus R3. You could have gone for columns as well. 5x plus 4. All the corresponding entries added into first row. Here also I am getting 5x plus 4. You can check it for the third element also. It's the same. Since there is no transformation in second row and third row, so they will be kept as such. No change. Now the next property says I can take a common factor out from any of the rows or any of the columns. So 5x plus 4 is common from the first row. The whole first row gives you a common factor out. 1, 1, 1 is ready. So we will start making zeros. The next operation will be C2 such that C2 minus C1. At the same time, I will go for the operation C3 such that C3 minus C1. Since C1 is being subtracted over here, so C1 cannot take the transformation in the same step, but it can be subtracted from another column. So let's start with this. 5x plus 4. You can see there is no transformation in C1, first column. So I will be writing down as such. Let's start with C2 subtraction C1. 1 minus 1 give you 0. X plus 4 minus 2x. That gives you 4 minus x. 2x minus 2x gives you 0. Next, C3 minus C1. This is C3 and this is C1. So 1 minus 1, 0. 2x minus 2x, 0. X plus 4 minus 2x gives you 4 minus x. Again, I've got the upper triangle as 0. When I say upper triangle as 0, I mean to say all the entries above the diagonal are 0. You can actually go for expansion. You will get the value of the determinant simply as the product of the diagonal elements in such case. So that is the product of 1 into 4 minus x into 4 minus x. You can actually verify with the expansion through any of the rows or any of the columns. So this is RHS. We had started LHS and reached up to RHS. So the question is proved. You can find out such more questions very easily in your board exams. Let's start with 10th question, second part. We have been given this question. We have to prove this determinant is equal to k square into 3y plus k. Let's start with the proof. Starting with the LHS. We will be using properties of determinants as we are doing its practice. I can see I want a factor 3y plus k in RHS. So as soon as I add all these columns, I will be getting that factor very easily. Y plus y plus y, 3y plus k already. All the corresponding entries of columns will be added into first column. First column is transformed, no change in second column or the third column. Single factor 3y plus k taken out from first column C1, because the properties of determinant says we can take a common factor out from any of the rows or any of the columns. 1, 1, 1 is ready, so we'll start making zeros. Our next operations will be like this, that we can make these zeros. Since R1 is being subtracted over here, so R1 cannot take the transformation in the next same step. So that's why I have kept R1 for subtraction only. It means I'm not going to change any element in R1. So I will write it first of all as such. Now I go for R2 such that R2 minus R1. 1 minus 1, 0. Y plus k minus y. Y minus y cancelled out. K is left. Here y minus y is 0. Corresponding entries have to be subtracted. 1 minus 1, R3 minus R1. 1 minus 1 gives you 0. Y minus y gives you 0. Y plus k minus y, only k is left. Again I am having a lower triangle as zeros. So in such a case, as I have told earlier also, when you have a lower triangle consisting of all zeros, that is all the elements below the diagonal are 0, you will get the value of the determinant as the product of the diagonal elements only. That is 3y plus k into k, that is k square. K square is a constant, so it should be written in front, k square into 3y plus k, and this gives us RHS. The question is proved. Now I'm going to start with question number 11, first part. We have to prove that this determinant comes out to be equal to a plus b plus c whole cube. I start with LHS. All the elements have to be written down very carefully. Give a look at the RHS. It says a plus b plus c. That factor can be made if I add all the rows into R1. You can see a minus b plus 2b. That gives me plus b. Minus c plus 2c. That is plus c. Similarly also here you will add the corresponding entries. Then you will get a plus b plus c. Only R1 is to be transformed, so no change in R2 or R3. These have to be written down as such. Properties of determinant tell us that we can take any common factor out from any of the rows or any of the columns. So I have taken a plus b plus c common from R1 and the remaining entries as such. 1, 1, 1 is ready. So we'll start making zeros. So the operation will be C2 such that C2 minus C1. At the same time, C3 such that C3 minus C1. The common factor out will be written as such only, no changes. C1 cannot have any transformation, so it has to be written down same, no change. Now I'm going to start with C2 such that C2 minus C1. 1 minus 1. 0. Corresponding entries have to be subtracted. B minus 2b, that is minus b. Minus c minus a. So it is actually minus of a plus b plus c. 2c minus 2c. Again 0. C3 such that C3 minus C1. 1 minus 1, 0. 2b minus 2b, 0. And when you subtract this, c minus 2c minus c minus a minus b. So again I have taken minus common a plus b plus c. You can see I can take a plus b plus c common from second column as well as third column. So I have taken it 2 times common. Already one time it was written outside. So it becomes a plus b plus c whole raised to power 3. And this is the remaining determinant. Since again I am getting the upper triangle consisting of all the zeros, that means the value of the determinant will be the product of diagonal elements. That comes out to be a plus b plus c whole cube, which is your RHS as required. So it gives you the proof of the question. This of determinants of properties of determinants, you will be able to score very well in your board exams, because one question for around 4 marks or 6 marks is quite expected all the time in boards. So keep on practicing, and let me know if you have any doubts in the comment section. Keep on watching my videos, enjoy it. Thank you for watching.